Hello, my name is Pedro, and on this video we're going to talk about our work on persistent memory and the rise of universal constructions. This is joint work done by Andreia Correia and Pascal Felber at the University of Neuchatel. Persistent memory is a new technology that provides a durable media with load and store access granularity. It has existed for many years in the form of battery-backed DIMMs, but it really never caught up. Capacities were around 16 gigabytes and they needed a bulky external battery. About a year ago this changed when Intel released its Optane data center persistent memory with capacities up to 3 terabytes per CPU socket. With persistent memory comes the need to have persistent data structures. These are data structures that survive a non-corrupting failure, for example, a power failure. Making a persistent data structure can be a challenging task. Some of the difficulties behind it are where to place the flushes and defenses, how to write a correct recovery procedure, how to allocate and deallocate in persistent memory efficiently and without leaks, or simply how to modify an existing data structure at a later time. When the goal is to obtain a data structure that is concurrent and persistent, there are three main roads to get you there. We can make a data structure by hand. This typically is complex and requires one data structure, one academic paper. Or we can apply a kind of recipe to an existing lock-free data structure. There are several different such recipes. Some are easier to apply than others, but they all require the pre-existing lock-free data structure. Or we go with the PTM approach, a persistent transactional memory that transforms sequential data structures into concurrent and persistent data structures. So far, one file was the only one that provided wait-free progress, all others were blocking. In summary, we can make a persistent and concurrent data structure by designing it from scratch. It's very hard to do correctly and usually requires an entire paper to describe the algorithm. Or we can take an existing lock-free data structure and apply some kind of recipe to make it persistent. Or we take a sequential data structure and do type annotation to use it in a persistent transactional memory. The PTM will take care of the concurrency and persistence for you, so you don't have to worry about it. We will now describe the logical components of the redo PTM and the steps taken during a write transaction. There is an array of atomic pointers and a matching array of bits used by early combining consensus. There is a ring buffer that acts as a wait-free queue to store the physical logs, redo logs, for each group of transactions. Each entry of the ring queue has a logical pointer to an entry in the states matrix. There are also T+1 combined instances, one per replica, and the replicas and the curcom pointer are located in persistent memory. In the first step, the thread announces its transaction by setting an atomic pointer to its own stud function where the transaction is located and toggling a bit. This is early consensus. Then it will read the current curcom pointer, save it in a local variable, and populate a state entry with the new values. It will then help append the head of the ring queue in case it's needed. This is similar to what the Michael Scott queue does for the tail. Then it will search for an unused combined instance and it will acquire its write lock to gain access to its corresponding replica in persistent memory. Then it will apply the redo log so that it brings it up to date to be similar to the replica to which curcom pointer is pointing, and in the meantime other threads may arrive, publish their own operations. Then it will go and aggregate all the operations and simulate them on the replica in place, and at the same time create an undo and redo log. This redo log is saved on its own state entry. It will then downgrade the combine to a read lock and flush all the cache lines that were modified on the replica. The last step is to do a compare and swap on the curcom pointer. If it's not successful, it will have to apply the undo log to revert those changes, flush them, and then restart everything. If it fails for the second time already, then it can simply return its result because it knows that its result is ready, it has been made by some other thread. And if it's successful, then now the curcom is pointing to its own replica and its operation is ready. This table compares one file with the cxptm and redo-ptm, both introduced in our paper. The main disadvantage of redo-ptm is that it uses t+1 replicas of the database, while one file has a single replica of the data, with t being the number of threads. On the other hand, transactions in redo-ptm do not abort. This non-abortable transaction property is similar to what multi-version concurrency control does for databases. While multi-version concurrency control is implicitly blocking for reclamation of objects and records, our technique is fully wait-free. There are 5 main reasons that justify the performance increase of redo-ptm over the previous approaches. The first is that we place as many as possible components of the PTM in DRAM, volatile memory. This includes the physical log. The second is that stores to the same location are aggregated into a single final store. Then each cache line is flushed a single time, and flushes are deferred to as late as possible and aggregated across groups of transactions. The fifth and final one is that we use non-temporal stores when making a full copy of the replica in persistent memory. The first of the factors that improve performance is that the replicas and the curcom pointer are all located in persistent memory, but everything else is in volatile memory. That means the ring queue, which is a memory-bounded kind of wait-free queue, the physical redo logs and undo logs that are used for the transactions, the combined instances associated with each replica. They contain the cache line logs, the reader-writer logs, and head pointers. All of these are volatile. In previous PTMs, like Mnemosine, the transaction is transformed into a physical redo log, described here in red squares. In redo-ptm, we don't do that. Instead, we use the combining consensus by RLI to aggregate multiple in-flight transactions into a single one and then create an undo-redo log of all of them. If there are stores to overlapping addresses, each of those addresses is written into a single time, which reduces write amplification. Again, classical redo PTMs like Mnemosine and OneFile, they flushed a persistent log. We don't have a persistent log, we have a volatile log. So what we do is, again, we combine every operation into a single one, and we create a combined cache line log of all the cache lines that have been modified. This means we only need to flush those cache lines, and we do it a single time. We call this flush. As mentioned before, in redo-ptm, we aggregate a group of concurrent transactions into a single redo log. However, we don't flush those modifications until we need to change the curcom pointer. The technique shown on the previous slide allowed us to aggregate flushes from transactions in the same group. This technique allows us to aggregate flushes from multiple groups of transactions. The fifth and last optimization is done when we need to make a full copy of the replica. This is a rare event. Instead of doing regular stores plus flushes, we execute non-temporal stores for an extra performance gain. On this slide, we show a sequential queue that has been annotated to be used with redo-ptm. The resulting wait-free queue is shown in the blue line, and as we can see on the left figure, it is capable of scaling thanks to the previously described optimizations. Queues made with other PTMs or even handmade lock-free queues have less throughput. We now show one other data structure, a red-black tree. Because of its strict balancing, it means the write transactions can be quite large, touching many different memory locations and different cache lines. Scalability here is not so good. For the hash set, redo-ptm is able to scale, plot below, even for write-intensive workloads, where half are insertions and half are removals. This happens because many of the modified memory locations are on allocator metadata, and the more threads means more operations can be grouped with the optimization techniques described previously. Making a wait-free and persistent queue is relatively simple with redo PTM. You write sequential code, you call our allocator and deallocator, and you wrap everything in lambdas that you pass to the PTM. With making a lock-free and persistent queue by hand is a bit more difficult. Here is the enqueue, the dequeue, the rest of the dequeue, and the recovery method. And in the end, redo PTM is faster than the handmade lock-free persistent queues. Up until today, key value stores have been made by taking a concurrent index data structure, adding some kind of concurrency control like two-phase locking, usually with multi-version concurrency control, adding redo log or some other technique for the durability, and then it would take several experts in concurrency, durability, and databases to combine all of this, usually with several years of work, to get a blocking key value store. With redo PTM, we made a database storage engine by taking a sequential data structure, instrumenting its types, and wrapping its methods in lambdas to pass them to the redo PTM. We chose a B tree, but other data structures could be used. Although the redo PTM itself required significant expertise in concurrency and durability, using the PTM to make a key value store required less than 2 months of work for a developer that is expert in databases, without having to know anything about concurrency or durability. The end result is a key value store that can also do dynamic, durable linearizable transactions over any annotated type. RedoDB is the world's first wait-free key value store, has no recovery, non-abortable reads like multi-version concurrency control, and provides ACID transactions written in C++. But is it fast? As it turns out, for reads, yes, it's extremely fast because read-only transactions do very little synchronization and will have their own replica of the database to go through without any contention. This plot shows RocksDB versus RedoDB with 10 million keys running on Optane DC persistent memory. Thank you for watching. If you want to learn more, you can read the paper, and the source code to the benchmarks and the wait-free key value store are available on GitHub.